Good evening and welcome everybody. This is Obi-Wan Pez for N-Simplex Pachinko. We are doing some differential equations tonight, and tonight's topic is on reduction of order and variation of parameters, which we have seen from the perspective of first-order systems, and now we'd like to look at this from the perspective of second-order differential equations. This is the full algebraic treatment that we're going to get from it. A bit of this is going to be probably a bit heavy, but that's all right. Coming in a bit later, we have enstucky, and Zach is off for the night, so we will be, we'll be working until whenever that happens. That's perfectly fine. I did last stream, anybody who was here literally last night, I have to think about that sometimes, I decided to take a question that had come up when Zach and Stucky were here like a month ago, when we were doing first order systems, and look, now that was only like a week or two. It's like 2 weeks. Which was, what exactly do we need when we have a non-homogeneous portion to our differential equation that ends up with a term that is a part of the null space, or at least partially a part of the null space. So typically what happens, in this case I went with t squared e to the negative 2t. If the null space had no e to the negative 2t term, then our particular solution for this one would be at squared times e to the negative 2t plus bt e to the negative 2t plus c e to the negative 2t. Or you could just factor out e to the negative 2t and have at squared plus bt plus c. It's a very nice quadratic that's then attached to our e term with our negative 2 eigenvalue. But since the null space has both an e to the negative 2t and it's a repeated root, so here we have a multiplicity of 2, we also need t e to the negative 2t. This means that we need to take hypothesis 2 here. We need to take our quadratic and bump it up by a degree such that none of those terms are going to be overlapping with our null space solution. So we can't have an e to the negative 2t term, and we can't have a t e to the negative 2t term. So here, with our quadratic at squared plus bt plus c times e to the negative 2t, we have to bump that up by a degree of 2 in order to make at to the fourth e to the negative 2t plus bt to the third e to the negative 2t plus ct squared e to the negative 2t. When we do that, we then take all this stuff, take both of its derivatives, put it into the original differential equation here. A whole bunch of terms cancel out, which made me feel very nice. And then we get all of our like terms on the left and the right side, which we got here 12a t squared plus 6bt plus 2c is equal to t squared. Our t squared terms have to match, so 12a has to be 1. Our 6b off the t has to be 0 because we don't have any here. And our 2c also has to be 0 because we don't have any here. When we solve those equations, b is c is 0, and a is 1/12. And then that means that our particular solution is going to be 1/12 t to the fourth e to the negative 2t in order to create that bit here. I also verified this on stream on Wolfram Alpha, so that went away, and all those little terms all went away just as I did here. I was kind of skeptical for about 5 seconds, and then once I saw Wolfram, it was like, yeah, everything is literally right here. We got all those terms and only those terms, so I was mollified by that fact. Our first hypothesis was, what if it was just at squared e to the negative 2t plus bt e to the negative 2t and plus c e to the negative 2t? But the problem with that is that once you get those terms, then we end up with bits that are going to be absorbed into the null space. So that creates a problem. If we didn't accelerate our terms such that the lowest term in the polynomial is now bumped up beyond the null space, right, by multiplying by our t-squared, then we end up with stuff that's going to be absorbed into null space, and then it's kind of an invalid solution. It doesn't really work. And if you tried plugging it into the differential equation, it would not get you t squared e to the negative 2t. It would just fail outright. So we do need that t to the fourth term, as we saw in the Wolfram thing. And as you can see here, if you can follow the algebra, this is also available on the Discord. So we're using Penn Center's Discord, and we are under class differential equations, forum, and class bits. So if you go in there, you can get that all sorted out. Okay. So for tonight, what we're looking to do is expand upon this idea of trying to solve differential equations using specifically our... We gotta get rid of all this stuff, so... I cannot just reset the canvas, unfortunately, because I started a session. Yay. Okay. Oh, yep. And we're back to the old Obi habits of not actually plugging the stuff in. Hey. Stooky!
Well, I do see that the escalator is up in the age, though, so I'll get myself in there.
Awesome. How you doing?
I'm doing well. How are you doing?
Yeah, we're doing alright. Didn't actually get, like, out today, which I think is, was a mistake. Kid went a bit stir crazy, you know? Alright. So, for tonight, we're going to start with x squared y double prime plus x y prime minus y is equal to 0. I'm going to assert that the first solution to this is that y1 is equal to x. This is for the... that was weird. Said it was out of room already. I don't think... Yeah, I don't have anything else here, so that doesn't make any sense.
Yeah.
Cool. And we will... Speaking of reduction... Alright, we will shrink this down like this. And so the question that first arises when we're taking a look at this is how to get the second solution, how to get y2. This is also... here, let's go like this. How would you classify this differential equation?
How would I classify the differential equation? That looks linear to me. Second order linear, homogeneous.
Right, and of course, if we back that up even further,
Ordinary.
right, the major classification, of course it's ordinary, because 99% of the ones that we're talking about, no, that's false. 100% of the differential equations that we start with are going to be ordinary. We're also not assuming in this particular class that anybody knows anything about partial derivatives. That's just a mechanism that we used in one of the earlier classes to talk about first order differential equations and how to get exact equations or prove exact equations. JJ's thank you for the follow. So the question again becomes, how do we solve for our secondary null space solution? Because, again, we're making a claim that someone figured out that our first solution is y1 equals x for our null space. Yeah. And we discussed earlier that we needed to have two solutions for our null space solution, given that we have a second-order differential equation. All right, so given that it was an assertion that y1 is equal to x is a null space solution, what might you suggest?
Maybe something like y2 equals xu? Kind of build from what we have.
Yep, so I would say our second step is going to be, let's suggest that y2 is going to be a function of x, in this case u of x, times our first solution. We have in all of our second-order differential equations talked about our null space solution in terms of like a linear combination of however many y functions we need to make this work. Again, second order, there are going to be two. Okay, and I would say even before you make this step, there should be something else that we do.
I don't know if we want to check that y1 is in fact a valid solution of the homogeneous equation.
Yeah, I'd say probably check the claim.
Okay.
So since y1 is x, y1 prime is going to be 1, and y1 double prime is going to be 0. So that makes it fairly easy to check. What do we get?
Just 0 plus x minus x.
Equals 0, so yeah, I think we could probably say that's true. All right. So we checked the claim. Yes, y1 is in fact just going to be x, and then y2 is going to be, instead of a constant times y1 or a polynomial times 1, we don't actually know what kind of function y2 is supposed to be. So we'll go with, well, it could be anything. So we'll say it's just going to be some function u of x times our y1. All right, in that case, what do we get for y2 prime and y2 double prime?
Y2 prime is u prime y plus y prime. y1. And then do it again. So u double prime y1 plus 2u prime y prime plus u y1 double prime.
same deal, but yeah. Okay.
Okay.
It's also going to help us out a little bit on second line here.
Yeah, to make that 2, 2.
Alright, so combine the two middle terms, we get that u double prime y1 plus 2 u prime y1 prime plus u y1 prime y1 double prime. Okay. Now we've done this in general, but it's even better for this particular gotta stop that, for this given null space solution, because we already have nice values for both y1 prime and y1 double prime. This is going to clean this up quite a bit.
Yeah.
So if we come over on this side, we could say that this is going to be u times x is our original y2. y2 prime then is going to be u prime x plus u, and here is x prime. So that's going to be our 1. And then again, y2 double prime, we're going to get u double prime x plus 2 u prime times 1, and then plus 0.
Yeah.
All right, now what?
Plug them in.
Woo! So we get from our original up top there. Oh, yep, go for it.
Okay. Can I see it? I can see it on the stream. Okay. So we have x squared times y double prime squared times now.
Sorry.
Okay. X times u prime x u, and then or minus the original. Which is gonna do something. U double prime x cubed plus u prime times 3x squared plus 0.
Sorry, where are we at the 3x squared? That is, you got 1 from there and 2. Yep, okay, cool. Yep, and the other two terms nicely subtract out, so ux minus ux. Cool. So, now we've got a differential equation, and what do you notice about it?
It's first order in u prime.
Yeah, okay, so can you explain that?
So the second derivative of u is the first derivative of u prime. So that's
Right, so if anybody hasn't seen it before, right now what we see is that there's no u term over here at all. And so we're just saying, like, well, What if u prime was the primary variable that we cared about? So if we went with like, let v be equal to u prime, oops, then v prime is going to be u double prime, and therefore we get v prime x to the third plus v times 3x squared is equal to 0. How do you feel about that differential equation?
Well, that looks pretty nice.
Right, because the left-hand side is what?
That's exact. I mean, it's also linear, but...
How do you mean exact?
Like in the usual sense. If you take... if you multiply through by dx, then you get q dv plus v squared dx.
All right, and if we backtrack that further through the derivative, and we say, okay, this looks like a derived... I mean, obviously it's a differential equation, but if we say, okay, this is a specific equation that has been derived to get this thing, we can actually get this thing fairly easily. What is it?
Sorry, are you prodding the product rule?
Yeah.
Yeah, like it has an integration factor of 1.
Right. So in this particular case, we don't need to like do any integration factors or anything like that. This is taking the derivative of x cubed times v. No games, no funny business, just that's it. Typically, I like doing the general derivative operator, d, not just so that I can joke with my students that J's x, JJ's x. Yes, so we're using Excalidraw, and I personally am using a Wacom tablet. I originally had a bamboo tablet, which was about the size of an index card, and since then we have upgraded to a much nicer version, which has a much higher screen resolution as well. I can't complain. The original one was given to me by my department chair, so she was just like, figure out how to use this. Like, all right.
Yeah.
Omnifudos. Good evening and welcome. Yep. Righto. So with this, we're going to then take our integral of both sides. We can say that this is on our variable, or yeah, independent variable x, so we get our dx's on both sides. And then on the left, that is just inverse operations, essentially. And we get x cubed times v plus, well, we don't need to here. Reason being, on the other side, an integral of 0 is just going to be a constant. So 0 plus c.
Yeah.
All right, and then to figure out what v is, simple enough. Divide through or leave it as c x to the negative third. Whichever way you want to do it, doesn't much matter, right? And then what?
Start back substituting. So, integrate that to get u.
Alright, so here. All right, what do we get there?
Minus 2 over x squared times c plus d.
Right, we still do need constant, and it's just got to be something different. So yeah, as long as we're keeping track of what these things are, what they all mean, and we don't think that this is a derivative for some reason, we're good. And then we also need the times. So here we're going to divide by the new exponent.
Right.
So -1/2 in front of that. We could argue that we want to just say that this is going to be like a different c, a different constant of integration out front, or we could keep it as this c and have the -1/2 out front. It doesn't really matter how we're doing it. However, right, what is u?
U is y2 over x.
Sorry. So, y2 is going to be u times y1, and y1 was x. If we leave it just, again, either let it be this or alter it in some other way. What do you notice about this solution?
So I noticed that it has a plus dx term, which we can probably get rid of because the original equation was linear, and so we can subtract off linear combinations of the other solutions.
Right. Since it's going to be a linear combination, the constants are just going to combine, and we don't need to worry about it. And furthermore, right, our real goal here was to figure out what kind of function is going to be, or is going to set up our fundamental set of solutions. So we don't even need the constants out front, like, immediately. We can just say, look, this is going to be a 1 over x type function, and then leave it at that. Again, if it's got a linear portion, that's just going to get absorbed into y1 as well, so we don't need to concern ourselves with it. So y2 is going to be something that looks like 1 over x. And then from our y1 that we listed up top was just y1 equals x. The principle of superposition tells us that our homogeneous solution, or null space, I left it as null space earlier, our null space solution is going to be a linear combination of those two things. So then that's just going to be c1 times x plus c2 over x, not y, c2 over x. All right, how we feeling?
Feeling okay. I'm thinking that I'm happy. I think I see why we're going to be able to make this v equals u prime substitution in general. Um, it's not clear to me, and perhaps it's not true, that the integrating factor is going to work out nicely in general, and I'm just trying to think what would mean if it didn't.
That's fair. So let's... Go ahead.
So there's... I guess, okay, so because it's 0 on the other side, this is, I guess, what saves you. Because even if you have to multiply through by something wild, you're still going to end up with e times a function, right? There's not going to be a c times a function plus something else, or the c in some weird place. Which is what I was hoping would happen.
Okay. Oh, good. Okay, so bit harder of an example, but x squared minus 4 times y double prime plus 4xy prime plus 2y is equal to 0. And claim is that y1 is going to be 1 over x minus 2.
Okay. Well, let's do it. Oops. I went somewhere else. Let me find you.
Usually a thing pops up at the bottom that says return me to the writing.
Well, I can also follow your cursor, so that saved us this time. But okay, so let's you want to check that y1 works? I'm gonna start there.
Sure.
Okay. Prime is equal to so that's x minus 2 to the power of -1. So I think I like that. And then positive 2 this time. Okay. Okay, and so then gonna make life slightly easier and notice that this is a nice factor. 2 over 2. Okay. Then 4x. I think that's a minus 4x over x minus 2 squared. And a plus 2 minus 2. Which is going to get a little bit of cancellation. These two terms. Yeah, thank you.
Save a little bit of time there.
Good. So we're gonna have 2 squared, and then upstairs we're gonna have 2x minus 4x plus 2x minus 4. That should be a plus 4. Okay, and yep, that's 0.
Very nice. Right, so we get all the polynomial stuff to be equal to 0, and then therefore it doesn't matter what we took out. Righto. So since we Now I've at least proven that y1 is a solution. What are we going to do for y2?
Try u over x minus 2.
Okay, so I will steal this stuff from over here.
Thank you.
It's going to steal some extra stuff, but you know what? We'll clean it up. It's fine. Right.
Okay. And so, I want to do here. We just kind of gotta go for it. So we'll plug in x squared 4 times I time double prime plus minus 2 prime over x minus 2 squared. I think I've got hasty on the powers. This is y1, so it has no power. Y1 prime has a power of 2, and that also means that coefficient is off. Yeah. Okay, and then two. All right. Plus 4x times minus 1 or minus, okay, no, did it again. U prime over x minus 2 flat plus u minus u over x minus 2 squared. And can we get the rest in here? I think so. 2u over minus 2. All right. So here's hoping there should be a u right there, but here's hoping these things cancel. And that's no such luck.
Alrighty.
I'm not sure if I buy it, so I'm gonna think for this a second.
Alright, so let's think about what this is doing. We've got x minus 2 from each of these things, which is going to go away. Leaving an x plus 2. Oops. Which then still needs to be multiplied in.
Right.
Hopefully that does it.
Hopefully that does it. Because we get to multiply. Yeah, there it is.
Yeah, that thing.
Yeah. So, I'm seeing it. The UX's, we're gonna get -2 of them from here. We're gonna get -4 of them from here.
So that one's going to be a... Oh, you're doing X,
yeah, I just
right.
put a minus sign there for no reason. No problem. Okay, and so that should be good. And then the constant terms, we're gonna get a 4u from here, right there, and then a -4u from down there. Very nice. So that was exciting, but...
Moment of panic is always the fun part. Oh no, what did I do wrong? No.
Okay, so let's handle the rest. So this, we're going to get a u prime almost by itself. Or u double prime, sorry. And then the u single primes, we're going to get 2x plus 2 from there, and then an extra 4x from there, so that's I bet that's not what's going to happen, but let me figure that out in a second. Plus 2. Well, no, I'm not happy with the plus 2 either. Okay. I think that plus sign should be a minus sign. And yeah, because that's a y prime, which has a minus sign, and it was positive in the equation, so I like that better. Okay, so then down here we're gonna get minus 2x plus 4x, which is 2x, and minus 4. X plus 4. It's making life difficult for no reason. Okay. And I would like to get rid of that x plus 2 immediately. So...
Sounds fair.
And so now we'll proceed, let v equal to u prime. So we have v prime plus 2v is equal to 0. In other words, v is equal to 2x. And then y2, or wait, no, one step, integrate that first. That first, so we get u is equal to c-ish minus 2x d. And so y 2 is equal to, well, I will take the liberty of throwing some constants away. I guess I didn't really need to do that. That is either right, or the x plus 2 should be on the other side. Y2 is equal to u times y1. Okay, I'm satisfied.
Alright, I'll go verify on the wolf from there real quick, but only because I got something different in my notes. Probably means my notes are wrong. It's fine.
Sure.
Yeah, I got a different solution. Okay.
Okay.
So I think that there may be something wrong with the differential equation that was extracted from here.
Okay.
So I got u double prime times x plus 2 plus 2 u prime.
Oh, interesting.
So let's just double check real fast what happened. X plus 2. That one there. So this was a minus 2, and then we had a plus 4x e prime, which were both over x minus 2.
Yeah, we don't get that extra factor of 2 from the derivative. So it's just that 2 is just coming from the form of y2 double prime. Four. I feel reasonably confident.
Let's go back and just double check the top. Wait a minute. That all got the same stuff. Oh, got it. This negative comes in. So that's going to make it a negative here.
Okay, yeah.
Which then causes the x minus 2 on the bottom to directly divide out. So technically, then we still have the x minus... No, not that one. This would still have the x minus 2 immediately, and then it divides out, and then that still leaves the x plus 2 here.
Got it.
Okay. Changes it a bit.
Yeah.
Alright, so that's going to be 2 over x plus 2 dx is going to be our exponent of this particular integration factor.
Oh.
Because then that's going to be 2 over x minus 2. Minus 2.
No, I think it's plus 2, right? That plus 2 comes from the other.
Yes, right. Okay, thank you. Sometimes don't know where my head is at, so it's all right.
Yep.
Alright, so this is going to be 1 over x plus 2 parentheses squared, and we need a negative out front. Nope, that's not, no. Other way. Right, we're taking the integral of this thing, so that's going to be 2 natural log. Absolute value x plus 2. Which is then going to be e to the natural log of parentheses x plus 2 squared. Which is just parentheses x plus 2 squared.
Okay.
And of course, in true first order differential equation, first order linear fashion, this becomes a very nice product rule. So u is going to be a negative 1 over x plus 2, which means that y2 is going to be, what was y1? 1 over x minus 2. We could just have that be y2 for this is going to be 1 over x squared minus 4.
Yeah.
Woo. Alright, so null space was 1 over x minus 2. And that's going to be c1 over that plus c2 is now over x squared minus 4. Alright, how are we feeling?
That works.
Alright, so this is similarly going to work for any sort of differential equation that we can then knock down into a first-order linear differential equation in our u prime variable. So we're going to be able to do that, and then we're going to be able to solve for what u is, and then we're going to need to sorry. We're going to need to multiply that by our original y1 and then get whatever our y2 is going to be. Again, find a linear combination of those things. In this case, we could actually say, we've got an x minus 2 in both of these terms and potentially factor stuff out. But I don't find it very valuable to do that. We're still saying, like, here's y1 and here's y2, and we want a linear combination of those two things.
Yeah.
But your mileage may vary, and discuss it with your professor. Any thoughts that you might have, Stuki?
Nope.
Okay. I think before we do the second half, I'd like to take a 3-minute break.
Sounds like a plan.
Alrighty. So thank you everybody for hanging around, and we will be back in 3 minutes. Just a little bit. Thank you.
Raiding party! Raiding party!
It's a chair raid. Rogan, thank you so much for coming in. Hello to everybody from Rogan's chat. I am Obi-Wan Pez, and this is N Simplex Pachinko, our home for mathy type stuff. Thank you so much for coming over and raiding in. Who else we got? Qui squared. Yay maths. Oh my goodness. Yep, so, actually, Rogan, what does VTUL stand for? It's Virginia Tech. Time travel to the year 1,000,1950. Nice. University libraries. Okay. Yep, so tonight
Yeah,
we're...
Sorry. I was being a bad press agent. I'm not subscribed, so I couldn't spam your emotes. But...
No worries. Actually, some of those are free. One? Maybe just the one? Is it yikes?
Oh yeah.
It's the yikes emote.
The yikes.
Yep, no worries. Everybody have fun with whatever you're doing, and thank you so much for coming on over. If you are here with Rogans and would like to stick around, definitely feel free and drop in any follows you want. So we are going to be talking about... the rest of our topic tonight is differential equations, and specifically, what do we do when we have non-homogeneous differential equations? With not nice. Homogeneous portions. No, the non-homogeneous. So...
I don't believe they exist.
You don't believe they exist? So the example that I use fairly often is, what if we just have y double prime plus... Nope, not y prime. Plus y is equal to the tangent of t. So our homogeneous portion, we can fairly easily figure out what's going on with all of its bits, and thought that was going to be the chicken dance for a second. Anyway, the homogeneous portion of this, the null space solution, is fairly easy to work with. This one we can figure out no problem. We'll do that real quick, but you notice that in the inhomogeneous portion, non-homogeneous, whatever you want to call it, we have a tangent, which we discussed at one point during our earlier exploits with first-order systems of differential equations, that this was not nice. It did not come up with a simple function that we could then say, okay, here's our function, derivative, and second derivative, such that if we take its second derivative and its original function, it's just going to get us tangent. So, like, it might be some form of secants and tangents, but it's not just going to be tangent, and it's not just going to be secant. So we have to figure out exactly what combination it is that's going to make this work.
Alrighty.
So if we go through our homogeneous portion, how do we do that?
Let's write down a characteristic equation. Looks like lambda squared plus 1.
Sounds good. So again, we let y homogeneous null space look something like e to the lambda t, or null space 1, I suppose, or null space character, whatever you want to call it, it's fine. First derivative is lambda e to the lambda t, and second derivative, oops, it's important notation, is going to be lambda squared e to the lambda t. Anybody who's coming in from Rogan's, again, thank you for any sorts of follows. And also, I do normal type maths on Tuesday, if anybody is interested in coming back and asking any sorts of questions, and some other nights whenever I feel like it. Mondays and Wednesdays are currently reserved for differential equations class. So if anybody has any interest in differential equations, please come on back on Monday, Wednesday. And Tuesday, again, Tuesday I'll probably be doing usually just any sorts of questions and answers that you want. If there's something that's always been kind of bothering you in the back of your head that's like, this never made sense for me, I will gladly take a look at it and see if there's any like alternative methods that I've learned over my 15 years of teaching at community college. It's going to help us out. Okay, so e to the lambda t is going to get factored out from the two terms that we're going to have plugged in, and then we just get lambda squared plus 1 is equal to, again, we want 0 for our null space solution. So in this case, we've got lambda squared plus 1 is equal to 0, so therefore lambda squared is -1, and therefore lambda, absolute value of lambda. Nah, I can't do that. I can't do that anymore.
Yeah.
Lambda is going to be plus or minus I. So we got a pure imaginary solution. This is going to get us a nice little null space. And we've already done this stuff before, so we could go through the derivation, but I'm not going to bother with it too much. Again, this is going to be either in the form of c1 e to the it plus c2 e to the negative it, or we could just say, look, we know what this is going to boil down to. The alternate form of this is going to be c1 cosine of t plus c2 sine of t. Technically, these are two different sets of constants, c1 and c2, but again, once we decide on a form that we're going to use, we can just reassign the constants to whatever names we want. These are going to be the fundamentals, so our cosine of t and our sine of t are the fundamental solutions, and then c1 and c2 indicate we're doing a linear combination of these things. Okay. So I had mentioned last time that here what we want to do is a bit different. Our particular solution, which has to be have its derivatives summed up in the same order as the differential equation above, need to be equal to the tangent of t. And so therefore, we would like it if this stuff had something to do with our null space solution. So the horrible Frankenstein term that I used for this was going to be a functional combination of the null space solution or fundamental set of the null space solution, rather than as the null space solution is a linear combination. All right, now that is an appropriate term. Functional combination is, like I said, just some Frankenstein term that I like cobbled together. So I have no idea if it's actually appropriate, but yeah, why not? So this is going to be u1 times the cosine of t plus u2 times the sine of t, and the u's in this case are both functions of t themselves. All right, so if we bring all this together, and we say we're going to use that in the original differential equation, this means that we need y particular prime and y particular double prime. Yay. What are we going to get?
Well, I don't want to say it. I know. Where are colors? There are colors. Okay. So we're gonna get u1 sine t plus u2 cos t, and I'm missing a sign somewhere. I'll fix it. Right there. And then u1 prime cos t plus u2 prime sine t. And okay. So nothing to it. Let's do it again. Minus u1 cos t plus minus u2 sine t. And then let's come all the way down here. U1 double prime cos t plus u2 double prime sine t. And then u1 prime. So we get u1 prime by differentiating this one, so we get to keep the minus sine t. And also from differentiating this one, so we get to keep the, that's another minus sine t. And u2 prime, same deal. We get it from differentiating that, so we get to keep the cosine t, and also get it from differentiating that sine, which is another positive cosine. Yeah, that's, could have predicted that, but we didn't. Okay. Let me just...
Alright, so I will say one quick thing, that at this point, right here, in our first derivative, what we can do is actually choose a convenient value, or initial condition.
Okay.
Such that u1 prime cosine of t plus u2 prime sine of t. Oh dear, hang on. Let's not make that look like double prime. Alright, such that that particular equation is going to be equal to 0. Alright, the reason for that is to clear out a bunch of the stuff in that middle row. To say, hey, I don't really want to deal with this.
Sure.
Quite frankly. So I should have stopped you beforehand. I apologize for that. But what's that going to do for y double prime?
It's going to kill the bottom term. Wait, it's going to kill the bottom term. Okay, yeah. And then get rid of those 2s.
So this is always the case, by the way, for any general... didn't say it ahead of time, but yeah, this is our variation of parameters. And something very similar happens when we're doing our first order systems, but we didn't notice any of this because we were just doing it all in matrices. Okay, so then we go back to our differential equation, which was again y double prime plus y is going to be equal to tangent of t. And substitute in the appropriate functions.
Okay.
Did you say that was a minus here, the u1 prime?
U1 prime, yeah, minus sine t.
Okay, and plus u2 prime cosine t, plus the original y, which again, y1, nope, u1. u1 cosine plus u2 sine. Equal to tangent of t. And we should notice at this point that we have our u1 cosine and u2 sine are in both these places here with opposite signs.
Strange.
For both of those, I don't think it's strange at all.
No, that's right. It's not strange.
Right. So this is realistically like the way that it works for each individual type of function. It's going to be manufactured this way.
Right.
So no matter what functions you're using or anything like that, as long as these are appropriate null space solutions for this differential equation, yeah, those things are going to clear right out. Because we've essentially just plugged in right, all of the stuff from the null space. We did not take any derivatives of the u's in this case. Right. So the u's are effectively just factoring out of this thing, and you're left with two functions which exactly are opposite each other.
Yeah.
So yeah, this is null space. times each of the u sub n's, whatever you want to call them. I should probably not say times. Alright, multiplied by u sub n. And then that leaves us with just the stuff from our particular solution, which is exactly what we want in the first place. So, works out very nicely. Here we get a negative u1 prime, u1 prime, sine of t, plus u2 prime cosine of t is equal to the tangent of t. And Stuki, can you solve this equation as it is right now?
Probably not.
Right, because we have too many variables in this particular case. We don't really care about the fact that t is a variable. What we care about is the fact that u1 and u2
Right.
are each functions of t, and therefore we won't be able to figure out what each of the functions are with only one equation. It's similar to, but legally distinct from, all of the discussions that we've had about linear systems of equations, going all the way back to, Algebra 1. So in order to be able to solve this, we're going to need a second equation, which, woohoo! What do you know? We have a second equation right here. Right? And it's not part of the null space. And it's an equation of on u1 prime and u2 prime, which are the same variables as what we had down here. So, like, this is... My goodness, who could have foreseen this? So, naturally, the original people who were trying to figure all this stuff out and worked out variation of parameters, I forget who it was, but the people who worked out variation of parameters in the first place, we're definitely going to look that up. Lagrange, and also Leonhard Euler. So Euler had his hands in it, but Lagrange finished it out in late 1700s, early 1800s. So we're going to make a system of equations that is in the variables u1 prime and u2 prime. And where do we go from here?
Well, I guess we could just pretend that nothing is wrong, and to our favorite methods for solving systems, solving linear systems.
Right, which would be?
Oh.
What would be something super convenient to multiply the top by?
Oh, okay. I mean, I'm not... sure, we can do... Cotangent? How good is that? Good enough. I'll take cotangent.
Okay. Not actually what I was expecting, but alright, let's go for it. Oh, right, because it... Yep, okay. I see it now. Right, so that's going to get us just bump right down there, and negative u1 prime cosine t, nice, plus...
something gross, u2... 2
prime, this is going to be cosine
squared
t over
yeah.
sine of t, which, whatever, we can deal with it, equals 1. And I forgot the prime there, but that's fine. Right, so then we can just add them up as is. It's going to be a 0. It's going to be...
We're making a comeback here.
u2 prime times the quantity, sine of t plus cosine squared of t over sine of t is all equal to 1. And then this is going to be a sine squared over sine. And that's also going to be a nice little identity right here.
Yeah. That u2 prime is sine of t.
Right. And so therefore,
I'm plugging that back into the orange. Oh, so you, sorry. Minus cosine.
yep. And so in this case, it would be probably helpful to just leave it with the negative and see what happens as we go through the rest of it. Just because this is our particular solution, it's not going to be a linear combination of stuff, so we can't drop a negative just because we feel like it, unfortunately. All right, then.
Then, take. I don't want to say this. Do this.
Yep.
Yeah.
That's so much nicer.
Cosine of t plus.
So this is also a note to
Prime.
other students who, may not have seen this before or have a habit of, I need to go back to the original equation. No, you don't. If you know, right, you don't even have to plug in u2. We know in this case that u2 prime is equal to sine of t. We've got all this stuff in terms of u2 prime. Obviously, just plug it in there. And then which one's it going to help the most? Well, if you multiply it by cosine, it's going to get sine cosine, so that's a little gross. If you multiply it by sine, it's going to be sine squared. Okay, maybe that'll work. But in this one, right, it actually just gets rid of your sine of t down here. So that makes it a bit nice. We're left with a cosine squared, which then also divides out when we shift it on over. With u1
I'm having doubts.
prime,
Yeah.
Where'd you get your
No, we need a
cosine of t? Yeah.
I see. Right, okay. I see why I was confused, but... so this is going to be 1 minus cosine squared of t over cosine of t. Which, since I'm going to want to integrate this, probably going to want to rewrite as secant minus, or secant minus cosine. Minus cosine.
Right, and then how do we...
Okay, so then u1 is equal to... or, wait. Which is minus sine of t, and then we look up integral of secant.
Natural log of. Absolute value. Yeah, secant plus tangent. I do that all the time too.
Okay, and so then
All you Calc 1 students need to know it, but... Right, so if we switch all the signs there, that's going to get us that stuff. Yep, plus sine t minus natural log of that stuff. Yep. Alright, and again, why don't we put a plus c on these?
That's a good question. Oh, because if the whole point is that we're multiplying these UI by null space solutions. So constant times null space is also null space.
Yep. So it's just going to get absorbed into the null space solution. We don't need to worry about it. It's fine. Right. Now what?
Finish the job. This,
Get our U2
U1.
there, get our U1 there. Oop.
Yeah, the U2 is the one that gets multiplied by sine. Okay. Oh, so, U2 that gets multiplied by sine. Okay. So yp is equal to u1. No. Yeah, u1 gets multiplied by cosine. 2 gets multiplied by sine. Can confirm. Okay, so I'm gonna write down the term I don't like first. And then that's, so we already multiplied the cosine, so we don't, got it. We need to add sine times cosine. And then we need to add u2 times sine, which is minus sine times cosine, and math.
Right, so very interestingly, in this case, we see that these terms end up going away, and we just end up with like the one term as our particular. That doesn't always happen. That's just kind of a neat little thing.
It feels like it's going to happen a lot, though.
Possibly.
Like, just because the thing, I mean, it's convenient to make this assumption, but there's no reason to think that like any sines or cosines are actually going to show up in the answer, right?
Right, and we still do in this case, just it's part of the other thing.
Right.
And it's not like it's just a straight cosine of t times a secant of t somewhere. It's this weird, like, there's a cosine of t, and then we've got a secant of t that's buried in a natural log function. So it's,
Right.
you know, it's really quite strange, I would say, from a first glance, that this would end up getting you tangent when you end up deriving it twice and then adding it to its original. But yeah, surprisingly, that's what it does. Okay, so I have posted a general form of this on our Discord, but I'm not gonna do it out in general. That's, you know, we got it.
Huh?
There is also the matrix form of this. So the way we had done this was we ended up with our negative u1 prime times sine of t plus u2 prime cosine of t equals tangent of t, and u1 prime cosine of t plus u2 prime sine of t. Is this where you were headed before? With looking at it in terms of matrices?
Yeah, I probably would have said that left to my own devices.
Yeah. So had we set it up as matrices, we get a negative sine t cosine of t, and cosine t sine of t multiplied by our solution vector u1 prime u2 prime is equal to tangent of t 0. So what we've actually done here is set up our fundamental solution matrix. So we got the fundamental of the null space.
Right.
And I think if we found eigenvectors, we would also find that it was negative 1, 1, 1, 1. I can't speak authoritatively about that, but I'm pretty sure that's right.
Yeah. And by the fundamental matrix, you mean the thing that we take the Wronskian of, right?
Yes. So if we were looking at
The determinant to get the Wronskian, yeah.
Right. Yep. Right, and Wronskian can't be equal to 0, so we could also check that if we were interested, but yeah. This is a negative sine squared minus cosine squared. It's going to get us a negative 1. So we're good there. And here we get our u prime vector. When we multiply these things together, this is going to get us our g vector, which was our general vector for the non-homogeneous portion. And so what we would want is u prime is going to be equal to, here we need to multiply both left and, both sides of the equation on the left by the inverse of our fundamental. And then from there, take the integral of both of those sides. Yes, they are vectors, which makes it a little awkward, but if you remember how to do that, right, then our u vector is going to be equal to that integral of the inverse fundamental times g dt. And that's going to depend on... Isn't it?
Thank you.
That's going to depend on all of our different factors. What do we have for our fundamental? What do we have for our g vector? And make sure that you do the inverse correctly. I know that most of the time we're just using like MATLAB or Wolfram to get these things. And it makes it a bit easier. Right. So, interestingly, you bring up the Wronskian. So, let's see. General solution that uses variation of parameters is that our y is going to be equal to c1y1 plus c2y2, of course, because we're always using the null space. And then we get plus y1 times the integral from t0 to t of negative y2 of, we're going to just use a dummy variable in this case, s times g of s all over the Wronskian in terms of s as a variable. ds plus y2 times the integral.
Okay.
Right, this is how you get all of those, like, this is, right, this stuff is u1. And then all this stuff here is going to be u2. Y1 of s times g of s, ds on the end, and Wronskian in terms of s on the bottom again. Now it was kind of convenient in this case that our Wronskian was just equal to 1 or -1, depending on depending on what order you put the equations in. Apparently I slotted the equations the other way, so I got a +1 when I did the Wronskian for my notes. But if we do look at this real fast, I'm not going to go all the way through, but nonetheless. This was going to be negative y2 in our case was the cosine or sine. Oh, I think it did sine. Sine of t times the tangent of t all over, we did -1 the way that we had it, and plus y2 integral y1 was cosine of t times tangent of t over -1 dt on both. So this one's going to be just easier to run with. This is going to be our y2 was negative sine of t times, this was sine over cosine times cosine. It's just going to get a sine. And then we take the integral, and that gets us a negative cosine. Whereas over here, we've got a cosine of t times the integral. This is our sine squared of t over cosine of t dt. Alright, and that's actually a secant tangent. Hang on. I screwed something up. Oh no, it isn't. Never mind. It's a sine tangent. Never mind. So those are not particularly compatible. So we make that 1 minus cosine squared of t up top. Or cosine of t, it's still taking the integral of that stuff. We still got a cosine on the outside. Right, integral of our secant of t minus cosine of t dt. So that should look familiar. Unless I messed up the sign, it should be the same thing that you got back here. Negative cosine plus secant. Yep. Cool.
Right. Yeah.
Alrighty. any particular questions on the... Yep. Any particular questions on variation of parameters that you can think of, or somebody else might ask?
Wow. Nope.
I will reiterate to everybody that this is like one of the most powerful methods that you could possibly ever learn. So variation of parameters is extremely powerful. It only fails under the circumstances where our integral is impossible. If you can't do it in closed form, then you're not going to get a closed form solution. But we will, in future days, see some examples of what happens when you can't get closed form, and we'll start talking about numerical solutions. Next class, however, we're going to look at some of the applications of second-order ordinary differential equations, which includes gravitational acceleration, including air friction, Kirchhoff's law. There's a bunch. Arc.
Springs.
Well, anyway, those are going to be important anyway. What'd you say?
Spring systems is the
Ring
other one that
system?
usually gets.
I don't think I know that one, so feel free to bring some expertise.
Oh, yeah. I'll get some vocabulary in order when.
Excellent. Thank you, because I definitely don't know it. Yeah. Is that like abstract algebra?
No. It's just, yeah, Omni is saying the right thing. It's a spring as in a physical spring.
Spring. Okay. I heard ring for some reason. So that makes much more sense to me now. Yes, spring mass systems. You can tell it's late. Okay, so yeah, spring mass systems, gravitational acceleration, and Kirchhoff's law being the RCL circuits are going to be like the big three. There's a bunch more applications that I could probably look something up and try to see if we can discuss a little bit about them. And yeah, apart from that, I think we'll see you on Monday, Stuki, if you're in.
Sounds good. Yeah, I expect to be.
Alrighty. And if you want to hype anything, feel free. You have the floor.
Sure. I guess I didn't get to do the intro, so yeah, I'm Ian Stuckey. I'm the host of the Mathematical Creature here on Twitch, as well as the organizer for No Railroad, a geometry study blog, as well as apparently a Javier Alvarez hype blog. So there's a post coming out probably tomorrow about some of the progress, including a particular poster on Mass Stack Exchange, who I've attracted some fondness for.
Very nice. Alrighty, well, I'm going to stay on a little bit, I think, and ask if anybody has any other questions, whether that be on differential equations or otherwise. Any other mathy type stuff, feel free and ask. I will put that in chat. I will spend the next 3 minutes or so probably taking the pictures of our board so I don't lose them, and then clear it off and see if anybody has any questions. So thanks so much, Stuki. I'll see you whenever you're streaming. Probably next.
Yeah, probably. Thanks for hosting.
Yep, no problem. Thank you. Right, and we're going to close out Discord. Alrighty, so yeah, like I said, I'm going to take the next 3 minutes do an ad break, catch all the stuff that I put on our board, and make sure that we've got that in pictures. Put that in Discord, maybe cycle some water if we got some time. So, see you in 3. And we are back. If anyone has any questions about mathy type stuff, being whatever level you want, right? It doesn't have to be differential equations. We'll do anything. Feel free and ask away. We will post that onto our yeah, well, it'll be Q&A session will be posted onto Twitch. This platform, you know, this one. Omnifetus. Stucky was at the University of Minnesota at some point or another. Whew. Oh, that one's spicy. Sorry, not your comment. I just came across a differential equation that was in our... Whew. That was in my notes here from, years ago. Some students had asked about something, and I was like, sure, let's do it. Cyclic actions in combinatorial invariant theory. Nice. I don't know anything about those. Woohoo! Right. Ooh, I forgot about that one. Abel's theorem applies in differential equations. So we have our... If anybody has any actual questions concerning math, feel free to interrupt me, because otherwise I will just do this all night. We end up with y1, y2 prime minus y1 prime, y2. And then the derivative of the Wronskian is y1 prime, y2 prime plus y1, y2 double prime minus y1 double prime, y2 minus y1 prime, y2 prime. Those are going to get knocked out. So Wronskian prime is equal to y1, y2 double prime minus y1 double prime, y2. In general, we have our differential equation. Yeah. So there's two forms that our differential equation usually comes in. Capital P, y double prime, plus capital Q, y prime, plus R, y, is equal to usually 0. At least when you're doing the homogeneous version. And here, that's all we're going to talk about. So this is fine. Or we do divide through by big P, and then we get y double prime plus lowercase p y prime plus lowercase q y equals 0. So if we plug this is a fun little quirk of differential equations. Let's also just check real quick here. More along the lines of algebra. Okay. Right, since y double prime is equal to negative py prime minus qy, and we can let that be both, right? Y1 double prime is equal to, comma, semicolon, something, I don't know, whatever, negative py prime minus qy1 in both cases, and y2 double prime is equal to negative py2 prime minus qy2. have Wronskian prime equal to y1 times y2 double prime, so negative p y2 prime minus qy2 minus y1 double prime is negative p y1 prime minus qy1 times y2. The y1, y2 terms here and here end up having opposite signs, and so they combine to be 0. So Wronskian prime is equal to negative p y1, y2 prime plus p y1 prime y2, which is equal to negative p times y1 y2 prime minus y1 prime y2, which I know, almost there. It's going to be equal to negative p times the determinant of y1, y2, y1 prime, y2 prime, which is negative p times the Wronskian itself. So w prime is equal to negative p times w, which it's a first order linear differential equation. Woohoo! Right, w prime plus p times w is equal to 0, which means that we get our standard, the standard stuff that we've been working with this whole time. So if w is e to the pt, if it's multiplied by e to the integral of p of t dt, then it's either going to take the derivative of w and leave the e alone, or it's going to take the derivative of the e term, which knocks down derivative of the integral of p, which is just p, times our Wronskian left alone. So now we've got, again, the derivative of Wronskian times e to the integral of p of t dt equals 0. Integrate both sides. We already did this with Stucky. It's the same stuff. We get into kind of a pattern of, oh look, it's exactly the same every single time. Realistically, yeah, pretty much. So the Wronskian is going to be equal to c times e to the negative integral p of t dt. So that's another way that we can express the, oh, it's gone now, but express the particular solution with variation of parameters, is that we can do that whole, oh look, it's the integral of, y1 times y2, this is all negative, g all over, and here we go, e to the negative integral p of t dt, instead of worrying about like what's the Wronskian. We already know what it is. Right, so then we do the same with y2 integral y1 g over e to the negative integral p of t dt. So Abel's formula, Abel's theorem, allows us to use this in much the same way that we had like in the systems of equations way back when we were able to use Kramer's rule. So this is very reminiscent of Kramer's. If not identical, I don't remember. Yeah, so the the one that I said, ooh, that's spicy, when I just looked at it, this was higher order. Was 6th derivative of x plus 3 times 4th derivative of x plus 3 times the 2nd derivative of x, which is just x double prime, plus x 0th derivative is equal to 3t squared sine plus cosine of t. So there is a way to do this. Since we have a split with addition, we can call each of these separate things like G1 and G2 and not have to do them all at once, but ends up working out fairly easily anyway. It's okay. So our characteristic here is just lambda to the 6th plus 3 lambda to the 4th plus 3 lambda squared plus 1. And this being a combination of 1, 3, 3, 1, this is something to the 3rd power. And the way that it skips on this, we end up with x squared, or lambda squared plus 1, all raised to the 3rd, is going to get us 0 as our characteristic equation. Then this is going to say that lambda is going to be equal to plus or minus I with a multiplicity of 3. So those are our 6 solutions, right? A positive 1, or a positive I, and a negative I, each with a multiplicity of 3. So with that, we can say fairly quickly, we don't need to go through like a whole bunch of calculations and stuff like that. We could just say that null space solution is going to be equal to, we are going to get a cosine and a sine with each of these terms. So we're going to have a constant term times a sine and a cosine, a linear term times a sine and a cosine, and a quadratic term times a sine and a cosine. So we're going to end up with like C1 plus C2t plus C3t squared times cosine of t plus C1 plus C2t plus C... Nope, I can't do 1. 1, 2, 3, 4, 5, and 6. T squared. Right, times sine of t. Right, so then our particular solution, we're looking at all this stuff over here. It has to start with saying, okay, well, they can have sines and they can have cosines. And we have up through t squared on one of them. So it's the sine, but in theory, we could take as many derivatives as we want on the sine and cosine and keep looping around and leave the t squared where it is. So it could be that term. I mean, obviously it is that term that's here, but we don't know which one it comes from. Does it come from a t squared times sine or a t squared times cosine? So yeah, we don't know. So we have to include that as part of our polynomial that we use for this. So we would say that this is like a plus bt plus c t squared times cosine of t plus d plus e t plus f t squared all times sine of t. But then we have to say, well, now we can't do this because this is all part of our null space solution. So now we have to say, well, how do we fix that? We take the entire particular solution and we multiply it by t to the, and again here we need to accelerate our constant terms higher than any term, being the highest term specifically, in our null space solution. So we can't use a t squared. We have to use a t cubed. So we have to multiply by t cubed in order to accelerate all these terms away from our null space solution. So then that's going to mean that y particular prime is going to be a is gone, so b plus 2c times the cosine of t minus, because we're going to take the derivative of cosine and get a negative sign, times a plus bt plus ct squared. This is the same thing that I did in my supplemental, but, you know, just want to show real quick a little bit of this. I'm probably not going to do the whole thing. Doesn't really matter if we do or not, you know. Wait a minute. No, I can't do that. We need the t cubed. Yeah, right. Let's just erase all that and start over. Right, so we're going to multiply all of this stuff by t cubed. So this is at cubed, which means that this is going to be 3at squared. Plus, here this was t to the fourth, so 4b t cubed. Plus, here this was t to the fifth, so 5c t to the fourth, all times cosine t minus at cubed plus b t to the fourth plus c t to the fifth all times sine of t plus, again, same thing here. It's just going to be with the other trig function. So 3d t squared plus 4e t to the third plus 5f t to the fourth. This is times sine of t. Come on. And this time it's plus d t cubed e to the fourth f to the fifth times cosine of t. Okay, so that's nice. That's the first derivative. Yep. And then we need y particular second derivative, and all the way down to y particular sixth derivative, which is not going to be that much fun. But then we get to plug in all the even ones up top into the original differential equation, and we eventually find out, right, sixth, fourth, second derivatives, and zeroth derivative, right, the original x. That was not supposed to be y's all over the place. Those were supposed to be x's. Cool. I've been using y all night, so makes sense, I suppose. Alright, this is going to expand actually very quickly due to the fact that every time we take a derivative, it's going to like increase the number of cross terms we have. So each of these are going to have fairly large coefficients at the end of it, which we could find, but yeah. I wonder. If I wanted to do this as derivative, is it 2 here? 1 here? I don't actually know how that would work. No. No, it doesn't know what I'm talking about. Okay. Okay, so can we just do parentheses? Somebody's got to correct me. Nope. Well, it's not Wolfram. That's alright. So if we go with y 6, y 4, y 2, y equals 3, 3, 1, right. Mm-mm. 3t squared sine. Plus cosine t. I did that. Yep. So we've got our C1 through C6, which are showing us the homogeneous solution, or null space solution, which are, as I said, polynomial times sine and cosine. And then we've got interesting, that's, yeah, anyway, it doesn't matter. 1/160th t to the 5th cosine of t, minus 3/64th t to the 4th sine of t, minus 1/48th t cubed sine of t, minus 3/16th t cubed cosine of t. So that, yeah, that makes it kind of interesting with that. Alrighty. Anybody have any other questions or questions that they would like seen, done out, anything like that? Any sort of mathy stuff you want to talk about? Be that math or be... Left my water in the other room. Hey guys, be that math or be it math education, be it just about anything else you want. Also, got my Eskrima sticks recently. So, these are pretty nice. 28 inches, I think. It's like basically the size of my arm. If I put my index finger right to the end, it tucks mostly under. I can wrap my fingers around the end if I tuck it into my armpit. But yeah, these are pretty nice. They're like I said, somewhere around 26, 28 inches, and like this is our we got some interesting martial arts techniques that we're learning. The other guy that I've mostly been working with is a black belt in Tetsudo, and I am a first degree brown belt in Tang Sudo. So a bit different, but at the same time it's like, you know, mostly the same stuff. Tang Sudo is a more Korean martial art, and I believe Tetsudo is Japanese, but it's very close in terms of a lot of the little nuances. So we've been practicing at our sensei's house. Has like a large, I say large, it's probably about the size of this room, like shed in his garden, so it's pretty cool. Stanford's into a lot of martial arts, yeah. So Tangsudo, the one that I've been working with, is was popularized by Chuck Norris way back in the day. And I don't know anything really about Tetsudo. There's also not like a lot of other karate type stuff where I am, or at least not ones that aren't like affiliated with a for-profit studio or something like that. I mean, they're pretty much all for profit, but you know what I mean. Ours was working out of the Parks and Rec department in our county. So they had they called up the county, our county, and the other 3 counties surrounding us, and got their classes on the Parks and Rec department sites. So you can go to any of the Parks and Rec locations and sign up for this particular martial art. And it works very nicely because they don't have any overhead in terms of maintaining a space. They can also run as many classes as they want on any night of the week. Basically one every night of the week, Monday through Thursday, in every county. And it doesn't rake in cash, but it at least maintains the sport itself. We don't have to worry about having we don't have to worry about maintaining a space. We don't have to worry about running out of room in said space. We just say, hey, we need a bigger venue, and the county is like, yeah, sure. So it's really cool just having been involved with this particular martial art for almost 20 years-ish. It's 18 or something. And then, of course, we subtract out the years for COVID. I was out for probably 2.5 or so. which really did not do me any favors. And now I'm going to be out for 3 years here in the UK. But like my sensei here for Eskrima said, you know, this is going to feed back. Your martial arts will feed into your Eskrima. Your Eskrima will feed back into your other martial arts. Yeah, your unarmed weapon or unarmed martial arts. So there's plenty of places in the UK. The problem is finding one that's a good fit, which, like, I was going to go completely, you know, completely off the rails and be like, hey, let's train in, they don't have JKD, what is it, Wing Chun. I want to study Wing Chun. So it's a style of Kung Fu. Okay, let's do, you know, let's try a completely different style that is very different from karate. And I, like, called their studio, I sent emails, I sent, you know, thing on their website, and never got a response back. So I was like, well, I guess they don't want me. And then I did this guy's studio for Eskrima, and he was just like, oh yeah, sure. Definitely got space, show up on this day. I show up and it's just me and one other guy. Like, alright. Yeah, and these are also 500 grams each, so essentially 1 pound. The sticks that we train with are either polycarbonate, and they're probably half this weight, so it's like 250, 200 grams, or they've got padded sticks, which are basically like a small rattan stick that's been wrapped in foam, and they weigh, you know, practically nothing. I mean, like 50 to 100 grams or something ridiculous like that. And we can whip these things around pretty hard. We're not trying to, like, those are 10 years in prison in California. Yeah, if you use them. Club weapons get a pretty nasty, harsh treatment. But I mean, trade-off, right? I can carry those around in my car. I mean, granted, I think they have to be not accessible to the driver, like, you know, similar to open bottles of alcohol cannot be accessible to the driver. Weaponry cannot be accessible to the driver. Sort of, yeah. But trade-off, right? I can carry those around in my car as long as they're not, like, immediately accessible from my position. But if I get caught with my lockpicking kit anywhere in the country, you are coming equipped, meaning that you are definitely going to steal something. They don't even question it. They're like, you're a burglar and you're going to steal something. We're sending you to jail. Oh, great. Yeah. There is a reason that I have this particular one. As soon as Bethesda said they were releasing the Vault Tech bobbleheads, I was like, absolutely. We were getting the one for lockpicking. That's the Pip-Boy from Fallout. So he's got his screwdriver and unlocked lock. That's unfortunately broken. It was glued into his hand, but it got snapped off at some point. Yeah. So Fallout 3 was like the big one. for most of us here in the platform. Yeah, not this guy. Fallout's a pretty good game. Number 3 I had problems with. I bought it when it first came out, and it worked fine. And then I bought a faster AMD graphics card, and like all animations were sped up. So I'm like, great, do I need to just... So I found out that I needed to like essentially underclock my PC. I needed to run graphics and intensive heavy programs in the background in order to offset the amount that it wanted to speed up. And I was like, I've been trying to find a fix for this for like 10 years. And nobody was able to do it. And then finally, it was like, I don't know, Windows 10 or something. They finally were like, oh yeah, by the way, we fixed this. So you can just like type in a simple command into the .ini file. Fixed it all right up. Like, couldn't have figured this out, 10 years ago. All right. If nobody seems particularly interested in mathy stuff, I'm probably gonna send out and then do a couple of chores in the background. So, thank you everybody for coming in. We have tonight. Okay. Let's see, who's on math? We got Admiral Stapler, who's doing some Sudoku. Who's that? No. Justin Helps is this guy who does some really interesting program type stuff. He's got many YouTube videos on like evolving these little blobs, and he makes simulations on evolution. It's a really good series. He does work with Godot and Blender. Stats in the Wild is doing uncontrolled variables, trying to work on slides for the next few days. Paleontologizing is looking at 60 years of understanding the species Deinonychus. Irish John Games is... Oh. Yeah, okay. He is celebrating affiliate-versary, and he's doing partner push. We'll do his. Irish John Games, also known as Jern. Jern also does, well, he's been working on a game called Rise of Piracy, and he's been doing good work on it, working hard, and just about, he's getting close to release on Steam. So he's also a friend of a couple of other people, including Science. Hope you all have a good rest of your week. I will be back on Friday for gamey type stuff and hanging around in other people's streams for the next couple of days. So, see you all later. My name is Obi-Wan Pez, and this is N Simplex Pachinko. Have a good night.